Let's go here. Right here it says application of capacitors. Right, that's section 8.5. Right. And so there are several examples. Well, let's go with this. This is the capacitor bank. As we said before, manufacturers, you know, they could be below that, but they're normally 50 kVR. Each of these boxes is a 50 kVR. You put them here. This is an oil switch. So this is a switch capacitor. So this probably is a 300 kVR, right? Remember on that figure I said 300 kVR fixed. Well, the fixed obviously won't have the switches. Now, if you look at that, there are basically what it says, the capacitor packs. Well, what it means is that what you got something like this, right? So the capacitor basically are, you know, if you have a capacitor that is rated 7,200 volts, right? You have to get there, right? So you don't have a single capacitor which is, oh, well, let me take it back. You know, when you buy a capacitor, says, well, the rated voltage is 450 volts. Well, that's the box, right, that you are buying the capacitor. Right, when you come here, this comes in a box, and that says 7,200 kilovolt, right, or 15 kV, whatever it is, right. But basically, it's made out of many segments that are connected in series, and then, in order to get the current, you connect them in parallel. And then you have to put a fuse. Why? Why do you put a fuse there? Right. It's called reliability. Right? You have to avoid that a failure in one of those capacitors bring out the entire bank. So what's happened is, if something goes wrong here, that fuse will blow. What's happened? Open, and what's happened? You isolate it. What are you doing? Minimizing the area affected by the fault, right? Have you heard that before? Right? Chapter 10, right? Same story. Common sense is called. Common sense 101, we need to have, teach a class on that. So you see, that's what, and here you have, and that's basically how the capacitor bank is being done. Now they have a lot of curves, which you are welcome to use. You know, here they have a table, right? They have a table that they say, well, if you calculate the reactive factor, right, and then the desired power factor, and this is the power factor, and you come here and you figure out what is the kW multiples, right? And basically all that comes from equations, right? Those tables are implementation of equations. So if you come to, if you look at the example, right, and I'm thinking about what is the test going to be. Well, the test is on chapter 8 and 9. And so what we are going to do is to calculate voltage regulation and power factor and the size of capacitor banks to have certain power factor correction. So if you look at here, this equation, you have seen it before, right? And then, well, in this case, what is this? Assume a 700 kVA load has a 65% power factor. Now you see why I'm using percentage on this chapter, because the book is using percentage. It's not saying 0.65. So 65. It's desired to improve the power factor to 92%. Using table 1, determine the following. Now, you're not going to be asked to use table A1. Right? Because what's happened? The tests are closed book, closed notes. Right? So unless that I photocopy that table, but really I'm not interested in the table. It's simple, right? You can understand that. And basically what it does, you know, in this case is the capacitor size is PLO times the correction factor, you know, and then basically here you have, and then, you know, then you calculate the size of the capacitor. The type of examples that you're going to see is more along the lines of that problem number 2, right? For example, assume that a three-phase 500 horsepower, 60 hertz, 4,160 V Y connected induction motor has a full load efficiency of 88%. Right? It's the same as the induction motor that you just saw right on the example, right? The only thing that the numbers, right, lagging power factor of 0.75 and is connected to a feeder. It is desired to correct the power factor of the load to a lagging power factor of 0.9 by connecting 3 capacitors at the load. Determine the following. Now, why are we specifying 0.9? That's right. Remember, that's the practice. The normal practice for the utilities is not to do to 100%, but to 90%. So you have that wiggle room, and you don't go into compensation. And then, so that's basically, you know, P, right? This is what we did, right? The equation, right? When we convert from horsepower to kilowatt and we divide by the efficiency, we calculate the reactive power, and then we calculate what is the reactive power. This here is the desired power, right? That's the desired power. And here we have that the reactive power provided by capacitor band is the difference, right? So, right? That's where we calculated the induction motor, right? The input power, right? And then basically you come and let's look at this. Here it is, right? That's the equation that is being used there, right? This is the desired, right? That's the desired value, which in this case is 0.9, right? So you calculate that. And here is, remember, the capacitor can be connected in delta or in Y, right? We saw that last time, right? And if you connect Y, right, this is floating sometimes. Why? Because you don't want current to go, the triple harmonics to go down there, right? Here, right, this is the current that you use Q, right? So what is missing there? That seems to be the question for S. Why there is no sign of theta? It is there. What's happened in the case of a capacitor? What is theta for a capacitor? 90 degrees. And the sign of 90 degrees is 1. That's the reason why it's not showing there. It's not used, it's using Q. And Q is the square root of 3 times the voltage times the current times the sine of the power factor angle. But bear in mind that in an ideal capacitor, the angle is 90. And so you calculate the current like we did in chapter, right? If you look at the voltage regulation notes, in some areas said materials from chapter 8, right? So you calculate like this gives you the capacitors, and there you calculate the typical equation for that, right? And then all this we did. Now, what can you object to the solution of this problem? See if you have been listening. See, when you are hired as an engineer, you have to have your own opinions, right? So what would you object to this problem? If you have to set 100 points in the test to criticize this problem, not likely, But what would you say that would you object to this problem that leads to the calculation of the reactance of the capacitor and then Z here, which goes on the other side? What would be the problem? This is the issue of that example, right? You must select a commercial size capacitor bank. The author is using 168.01 kVR. Well, where are you going to buy it? It doesn't exist. That's the main problem with that, right? So if I have to be, obviously I'm trained to grade problems and do things, so, but that's the problem, right? Is that a multiple of 50? No. So what would I select? 3 boxes of 50 kVR each, right? That's what I would select here. And then I can connect them in parallel, sorry, in delta or Y, but it will be 3 boxes of this. The picture will be the same as this, only 1 box on each slot, on each face. Right? If you go and work and you say this is the capacitance boss, the boss is not going to be very impressed, right? Because 168.5 does not exist. So that's my only problem with this, right? That's the reason why I have an example there that does is different, right? Obviously, if you have a delta or Y, the C is different, and here is calculating for the delta, and then if you multiply by 3, right, you should multiply by 3, right, to get, you divide the reactance by 3, right, to go from delta to Y, but remember it's 1 over omega C, so the other is multiply this, that's the delta, the C gets multiplied because it's 1 over omega C. What I've done on some of these things, let me see what is this problem. Right. So if you look at this, right, it's a 2.4 kilovolt. I have added the feeder impedance, right? So we can calculate voltage regulation. What's happened with this? Oh, it's a single phase, right? Right, that's what I say. What do you mean here? What is the square root of 3? Right. Well, it's a single phase. And this, right, what is the line-to-line voltage? The standard line-to-line voltage to 2.4 is 4,160.